Hello and welcome to lecture 28 of our Essentials of Semiconductor Device Physics course. In this lecture we continue our mathematical analysis of the p-n junction in equilibrium. Okay, so last time we proved this identity, and this time we're going to use this identity and the condition of equilibrium for currents to prove the condition of equilibrium for energy. So recall that this is the statement that the electrostatic potential difference compensates the chemical potential difference so that the Fermi level is constant across the junction. So we're going to prove this relationship rigorously using the condition of equilibrium for currents. Okay, so we need to define some new terminology. This region where the ions charges were exposed and where the electric field is concentrated is called the depletion region. So W is the width of the depletion region. And we're gonna set the coordinate coinciding with the beginning of the depletion region and another coordinate coinciding with the end of the depletion region, and we're gonna denote the first coordinate as minus xp. Here it doesn't matter if xp is positive or negative, but in the next lecture we're going to set the origin to be at the interface between the two types of ions. So you can already think of xp as being a positive number, so this is a negative coordinate, it's to the left of the origin. And this will then be a positive coordinate, and the width of the depletion region then is given by xn plus xp. And also recall from electrostatics that the potential difference between 2 points is given by the negative of the work done by the electric field. So this relation here comes directly from electrostatics, and this is just the application of the general relation between potential and conservative force, but applied specifically to the electric field. And if we want V naught, by definition V naught is the difference between the potential in units of volts on the N side and on the P side, like represented here. So since this potential does not change after this point and does not change before this point, because the electric field is concentrated only in the depletion region, then V naught, using the coordinates that we defined, is given by the potential at the point xn minus the potential evaluated at the point minus xp. So we're going to use this expression here to prove this identity. So in the previous lecture we used the condition of equilibrium of currents, and we used this condition for considering current of electrons. So to change a bit in this lecture, I'm going to use the same condition but now for holes. So we're going to consider a drift current of holes and a diffusion current of holes. So here we have the relevant equations. They are very similar to the ones we discussed in the previous lecture. So here we have the drift current is given by this expression. Then the concentration of charges can be expressed in terms of the concentration of holes like this. Then we use Ohm's law to express the drift current in terms of the electric field. Notice that now the average velocity is parallel to the electric field. It's in the same direction of the electric field because now the charge is positive. And we also have the expressions for the diffusion current. So using this, we're going to use this expression and this expression over here. And we also need the expression for the concentration of holes in terms of the Fermi levels that we derived in lecture 25, and we also need the expression that we derived in lecture 27 giving this identity. Okay, so we can use this expression for the drift current, this expression for the diffusion current, so we end up with this condition of equilibrium. And then we can move this term to the other side and use this equality here for dq. So using this equality we get this condition here of equilibrium, and then we can solve for the electric field. So now we have an expression for the electric field which depends on the concentration of holes, and the variation of the concentration of holes with respect to space. Okay, so we've just found that the condition of equilibrium entails that the electric field depends on the concentration of holes like this. So this expression is very convenient for our purpose because we want to connect the, the electrostatic potential difference with the energies. So here we have an expression that connects the potential difference with the electric field. And now we have found that the electric field depends on the concentration of holes like that, and the concentration of holes depends on the energy. So we can use this expression here for the electric field to connect the electrostatic potential difference with the energies. So we just use this expression over here, then we get this integral for the electrostatic potential difference. To evaluate the integral, we can take this term out of it because it's constant, and we can notice that this term is the derivative of the natural log of p with respect to x. So here we have the integral of derivative, so of course the result must be the log of p. So this is the result of the integral. We have the log of the concentration evaluated at the point xn minus the log of the concentration evaluated at the point minus xp. Then we can swap these two terms to get rid of the negative sign, and then we get this expression for V naught. And now we can re-express this term in terms of the log of p evaluated at minus xp divided by p evaluated at xn. Okay, now we clean the screen a little bit to evaluate this ratio explicitly in terms of the Fermi levels. So recall that this is the concentration of holes evaluated at this position, and this is the concentration of holes evaluated at this position. But the only term here that it depends on space is the intrinsic Fermi level. So the physical Fermi level must be constant across the junction, so it cannot be a function of x. This is why here we are expressing the intrinsic Fermi level explicitly as a function of x evaluated at the position minus xp, and the same goes here. So this Fermi level and this Fermi level is the same, and this difference is the difference between the dashed line and the blue line here. This difference is the difference between the same dashed line and the blue line here. And of course, you can cancel the concentration of holes in an intrinsic semiconductor. These are the same, and we end up with this expression. So we can take this exponential and move to the upper side, to the numerator, so it picks up this positive sign. And here we have the log of an exponential, which allows us to extract the argument of the exponential. So here we got rid of the log of the exponential by extracting all of these terms, which are the argument of the exponential. So we end up with this expression for V naught, and now this term here, we're going to get rid of the negative sign by swapping positions. So we end up with this term. It's the same as this, but now without the negative sign because we swap position, and this term we maintain. So this is the same here. So we finally got this expression here for V naught. And now we need to analyze what this means. So we're going to focus attention now on the meaning of this expression. Okay, so first of all, recall that this term is the blue line evaluated at this point minus the dashed line evaluated at this point. But since the band structure is not bent to the left of the dashed line, in other words, it's not bent in the P region because the electric field is concentrated in the depletion region, that means that this term here is constant from this point to the left. So we can identify this term as being the difference between the intrinsic Fermi level and the physical Fermi level in a p doped semiconductor, like we are representing here. this green arrow here is the same as in here because the lines are constant. And we can make we can reach the same conclusion when we analyze this term. So this term is the dashed line minus the blue line in this point. Since the band is not bent from to the right of the dashed red line, so this distance, this difference is constant, so it's also this difference here. In other words, it is the difference between the physical Fermi level and the intrinsic Fermi level in an n-doped semiconductor. Now let's recall how the band structures of a p-doped and n-doped semiconductor looked like before the junction was formed. So recall that this band here is just a copy of this band, but showing only this line, this line, this line, and this line. So we just copy this over here, and we copy this over here, and the only difference is that in the p-n junction, this band is lowered with respect to this one until the Fermi levels align. So that means that the relative distance do not change. So this distance here must be the same as this distance because this band is the same as in here. After all, this is a p-doped semiconductor. And this band here is the same as this one. After all, this is an n-doped semiconductor. Only that here, the overall band energy was lowered. But since the relative positions of the energy levels do not change, that means that this distance here must coincide with this distance, and this distance here must coincide with this distance. That's what we are representing here. So this distance is the same as this one, this distance is the same as this one. Since this term coincides with the length of this arrow, and this term here coincides with the length of this arrow, and we are adding these terms, we are adding this arrow here with this, which is given by the difference between the Fermi level of an n-doped semiconductor and the Fermi level of a p-doped semiconductor before the junction was formed. In other words, the sum of this term and this term gives this term, which is exactly what we set out to prove. So we set out to prove this identity, which is identical to this one, with the fundamental charge here in the denominator and here on this side. So with that, we conclude this second video about the analysis of p-n junction in equilibrium. And in the next and last video about p-n junctions in equilibrium, we're gonna describe the electric field dependence on space, and we're gonna calculate the width of the depletion region explicitly in terms of the concentration of doping atoms. So I see you next time.